Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the frozen mathematics of Saturn's rings. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Nearly 1.5 billion kilometers from where you rest tonight. Sunlight takes 84 minutes to reach a structure so vast it could contain our entire Earth within its inner gaps. Saturn's rings stretch across 282,000 kilometers of space, yet measure no thicker than a few hundred meters, a cosmic razor blade made of countless ice crystals, each one tumbling in its own precise orbit around the pale giant below. Only took 4.5 billion years to arrange this celestial jewelry display. The rings catch photons that left our sun an hour and 24 minutes ago, reflecting them back across the solar system in wavelengths that reveal their deepest secrets. Radio telescopes on Earth detect these whispered signals, measuring how the ice particles scatter radiation as they spin through the vacuum. Each crystal reflects light according to its size and composition, creating a symphony of electromagnetic echoes that speaks of water older than Earth's oceans. The particles themselves remain oblivious to their role as cosmic transmitters, broadcasting their properties across interplanetary space with every reflected photon. Scientists measure the ring's opacity through stellar occultations, watching distant stars dim and brighten as ring material passes between the star and observing spacecraft. The light curves reveal density variations precise to the kilometer, mapping structures that change shape over decades yet maintain their overall architecture across millions of years. A single occultation can provide more data about ring structure than years of direct imaging, as starlight probes the rings with a precision no camera can match. Only the rings know why some regions remain nearly transparent while others block starlight completely, creating patterns that shift like slow-motion weather systems made of ice. The gossamer nature of this system defies intuition. If Saturn's rings were compressed into a solid sphere, that sphere would measure only 100 kilometers across, smaller than most asteroids, yet spread across a distance greater than 2/3 the span between Earth and its moon. The individual particles, ranging from dust grains to house-sized boulders, maintain their orbital dance with a precision that makes atomic clocks seem crude. Each piece of ice follows Kepler's laws with mathematical perfection, creating patterns visible from space yet invisible to the particles themselves. The irony persists that this most delicate of cosmic structures orbits one of the solar system's most massive planets. Modern infrared spectroscopy reveals that ring particles consist of nearly pure water ice, contaminated by less than 5% rocky material. This purity suggests the rings formed from a relatively recent catastrophic event, perhaps the destruction of an icy moon that wandered too close to Saturn's gravitational embrace. The ice crystals tumble slowly as they orbit, their surfaces alternately heated by distant sunlight and cooled by the cosmic background radiation, the leftover warmth from the universe's birth. Now measuring just 2.7 degrees above absolute zero, each particle experiences temperature swings of 60 degrees Celsius as it rotates through Saturn's shadow, expanding and contracting in the vacuum like a frozen heartbeat. The Cassini spacecraft spent 13 years studying these rings, sending back images that revealed structures no ground-based telescope could resolve. Its radio science experiment measured ring particle sizes by analyzing how they scattered radio waves, discovering that most particles range from centimeters to meters across about the size of snowballs to small cars. The spacecraft's final dive through the ring plane in 2017 directly sampled ring material for the first time, detecting organic compounds that may preserve chemical signatures from the early solar system. Only then did scientists realize the rings contain a library of ancient chemistry, written in ice and scattered across hundreds of thousands of kilometers. The physics governing ring behavior operates on multiple scales simultaneously. Individual particles collide gently at speeds of millimeters per second, their impacts cushioned by surface frost that acts like cosmic bubble wrap. These collisions dissipate orbital energy, causing particles to spiral slowly inward towards Saturn, a process so gradual that the rings lose only centimeters of radius per million years. Meanwhile, gravitational resonances with Saturn's moons create gaps and density waves that propagate outward at kilometers per hour, reshaping ring structure faster than mountains rise on Earth. Ring particles experience a unique form of existence, neither fully solid objects nor fluid streams. They behave like a granular material, something between a liquid and a gas flowing around obstacles while maintaining discrete identities. This creates phenomena impossible in terrestrial physics: spiral density waves that travel at constant speeds regardless of the medium they traverse, and collision chains that propagate through the ring system like dominoes made of ice, each impact triggering the next in a cascade that can span thousands of kilometers. The electromagnetic environment within the rings remains largely mysterious. Saturn's magnetic field threads through the ring plane, creating complex interactions between charged particles and ring material. Plasma ionized gas stripped from ring particles by impacts and solar radiation follows magnetic field lines in ways that remain poorly understood. Electrostatic forces can levitate dust particles above the ring plane, creating temporary clouds that appear and vanish according to patterns that seem to follow no earthly logic. Perhaps the rings generate their own weather systems made of charged dust and magnetic fields. Temperature variations across the ring system create their own subtle dynamics. Particles in the dense B ring remain warmer due to frequent collisions, while those in the sparse outer rings cool to near absolute zero between impacts. These temperature differences affect how particles stick together during collisions, influencing the size distribution of ring material over geological time. The thermodynamics of ring evolution operates like planetary climate change, but compressed into a layer thinner than Earth's atmosphere, yet spanning a distance greater than that between Earth and its moon. Only a cosmic accident could have created conditions so precisely balanced that they maintain this impossible thinness across such vast distances. Among the countless particles that compose Saturn's rings, a hierarchy of gravitational influence shapes the cosmic architecture. Small moons, some no larger than cities, orbit just beyond the ring system's outer edge, their modest gravitational fields reaching inward to sculpt boundaries with mathematical precision. Prometheus and Pandora. Shepherd moons of the F ring measure only 148 and 104 kilometers across respectively, yet their gravitational whispers maintain one of the solar system's most dynamic ring structures across millions of orbital cycles. These shepherd moons operate through a mechanism so subtle it took decades for astronomers to understand their influence. Prometheus orbits slightly inside the F ring's orbit, moving faster than the ring particles according to Kepler's laws of orbital motion. As it approaches ring material from behind, its gravity accelerates the particles, pushing them into higher, slower orbits. Meanwhile, Pandora orbits outside the ring, moving more slowly than the ring particles, and its gravity decelerates them as they catch up from behind, pulling them into lower, faster orbits. This cosmic dance confines the F ring to a narrow band just 50 kilometers wide, suspended between two gravitational influences that never touch the particles they control. The precision required for this shepherding process borders on the miraculous. Prometheus completes its orbit in 14.7 hours, while the F-ring particles take approximately 14.9 hours to circle Saturn. This slight difference means Prometheus laps the ring material once every 25 days, creating periodic disturbances that ripple through the entire ring system. Computer simulations reveal that without these shepherd moons, the F-ring would spread outward and dissipate within a few million years, a cosmic eye blink compared to Saturn's 4.6 billion year age. Only the universe could design a system where objects smaller than most asteroids maintain structures larger than Jupiter's diameter through nothing more than gentle gravitational nudges. The shepherd moons themselves experience orbital evolution as they interact with ring particles. Each gravitational encounter that confines ring material also affects the moons, causing their orbits to slowly change over geological time. Prometheus drifts outward at a rate of several meters per century as it exchanges angular momentum with ring particles, while Pandora's orbit shrinks by a similar amount. These orbital migrations occur so slowly that they remain barely detectable even with decades of precise measurements, yet they represent fundamental changes in the Saturn system's architecture that accumulate over millions of years. Beyond the F-ring, other small moons carve gaps in the main ring system through orbital resonances, gravitational relationships where ring particles orbit Saturn in precise mathematical ratios compared to the moon's orbital periods. The Cassini division, a 4,800-kilometer gap between the A and B rings, exists because particles in that region would orbit Saturn exactly twice for every orbit of Mimas, Saturn's innermost large moon. This 2-1 resonance creates a gravitational environment where ring particles cannot maintain stable orbits, leaving a zone nearly devoid of material despite being surrounded by the densest ring regions in the entire system. The physics of orbital resonances operate like invisible barriers in space, preventing particles from occupying certain distances from Saturn while concentrating them in others. These resonances create a complex landscape of forbidden and favored zones that extends throughout the ring system, giving rise to hundreds of narrow gaps and dense ringlets that appear and disappear based on subtle changes in gravitational influence. Some resonances clear gaps completely, while others create locations where particles accumulate into narrow, dense bands that can be only a few kilometers wide yet persist for millions of years. Smaller shepherd moons embedded within the ring system itself create some of the most intricate structures visible in high-resolution images. Pan, a walnut-shaped moon just 35 kilometers across, orbits within the Encke gap in Saturn's A ring, sweeping up ring particles that drift into its path while simultaneously preventing the gap from closing. The accumulated ring material creates a distinctive equatorial ridge around Pan's middle, giving it the appearance of a cosmic walnut or a tiny planet wearing a belt made of its own captured debris. This moon demonstrates how even the smallest gravitational influences can create lasting changes in ring structure when given sufficient time to operate. The gravitational interactions between rings and moons operate on multiple timescales simultaneously. Short-term effects, such as the wakes and disturbances created by shepherd moons, appear and evolve over hours to days. Medium-term changes, like the gradual migration of gap edges and the evolution of spiral density waves, unfold over years to centuries. Long-term processes, including the orbital evolution of the moons themselves and the overall spreading of ring material, require millions to billions of years to complete. Only a system this ancient could develop such intricate clockwork, where every component influences every other component in an endless cascade of gravitational cause and effect. The shepherd moon's surfaces bear witness to their role in ring dynamics. Prometheus shows evidence of impacts from ring particles that occasionally escape their confined orbits, while spectroscopic observations reveal that both shepherd moons have compositions similar to ring material itself, nearly pure water ice with traces of rocky contaminants. This compositional similarity suggests the moons and rings share a common origin, perhaps forming from the debris of a larger moon destroyed by tidal forces when it wandered too close to Saturn. The irony persists that the very objects responsible for maintaining ring structure may themselves be remnants of the catastrophic event that created the rings in the first place. Modern computer simulations reveal that shepherd moon systems represent a delicate balance between order and chaos. Small changes in the moon's masses, orbits, or the amount of ring material can dramatically alter the entire system's behavior, sometimes leading to the complete loss of ring confinement or the collision of shepherd moons with each other. The fact that Saturn's shepherd moon system remains stable suggests either remarkable fine-tuning in the initial conditions that created it, or perhaps that we observe the system during a brief period of stability in a longer cycle of ring creation and destruction. The moons themselves remain silent witnesses to these cosmic processes, their cratered surfaces recording impacts that span geological ages, while their gravitational fields continue to shape ring structure with the patience of astronomical time. Between Saturn's A and B rings lies a gap so wide that Earth's moon could orbit comfortably within its boundaries. Yet this emptiness exists not through any physical barrier, but through the mathematical certainty of celestial mechanics. The Cassini division stretches 4,800 kilometers across the ring plane, a zone nearly devoid of particles, despite being surrounded by some of the densest ring material in the entire Saturn system. This cosmic void demonstrates how gravitational resonances can sculpt space itself, creating invisible architecture that persists across geological ages. The division exists because particles orbiting within this region would complete exactly 2 orbits around Saturn for every single orbit completed by Mimas, Saturn's innermost major moon. This 2-1 orbital resonance creates a gravitational environment where ring particles experience periodic tugs from Mimas that gradually alter their orbital energy, either pulling them inward toward the B ring or pushing them outward toward the A ring. Over thousands of orbital cycles, these repeated gravitational encounters remove nearly all material from the resonant zone, leaving behind a gap that appears as empty as interplanetary space, yet remains dynamically active on timescales invisible to human observation. The physics governing this resonance operate through a mechanism that would seem familiar to anyone who has pushed a child on a swing, just as small. Precisely timed pushes can build a swing's amplitude to dangerous heights. Mimas's gravitational influence provides regular, small accelerations to ring particles at exactly the right orbital intervals to gradually increase their orbital eccentricity. Particles that develop too much eccentricity eventually cross into regions where they collide with other ring material or escape the resonant zone entirely, leaving behind the mathematical emptiness that defines the Cassini division's boundaries. This gravitational clearing process operates with extraordinary selectivity, removing particles from the resonant zone while leaving adjacent regions virtually untouched. The division's edges remain sharp to within a few kilometers, creating boundaries so precise they appear almost artificial when viewed in high-resolution images. The B ring's outer edge, in particular, shows structure so complex and finely detailed that it resembles the edge of a vast cosmic saw blade, with individual features that remain stable for decades despite the constant orbital motion of billions of ring particles. Only the universe could create architecture this precise, using nothing more than invisible gravitational forces operating across millions of years. Within the seemingly empty Cassini division, careful observation reveals a sparse population of ring particles organized into narrow, faint ringlets that follow their own complex dynamics. These ringlets exist in locations where particles can maintain stable orbits despite the overall resonant clearing, creating islands of material within the gravitational desert. Some of these ringlets show elliptical shapes that rotate around Saturn like slow-motion whirlpools, their particles following orbits that precess at rates measurable only through years of careful observation. The ringlets demonstrate that even within zones cleared by resonances, gravitational dynamics can still support ring material under precisely defined conditions. The mathematical precision of resonant gaps extends throughout Saturn's ring system, creating a hierarchy of divisions and gaps at locations determined entirely by the orbital periods of Saturn's many moons. Computer calculations can predict exactly where these gaps should occur based on simple ratios between orbital periods. Yet the actual clearing process requires millions of years to complete and depends on subtle factors such as the thickness of ring material and the efficiency of interparticle collisions. The ring system thus represents a vast natural experiment in gravitational dynamics, where theoretical predictions can be compared directly with observed reality across spatial scales ranging from kilometers to hundreds of thousands of kilometers. Mimas itself, the moon responsible for the Cassini division's existence, orbits Saturn at a distance of 185,820 kilometers, roughly half the distance between Earth and its moon. This small, heavily cratered world measures only 396 kilometers in diameter, making it barely large enough for its own gravity to pull it into a roughly spherical shape. Despite its modest size, Mimas's gravitational influence extends throughout Saturn's ring system, creating not only the Cassini division, but also numerous smaller gaps and density variations that reveal themselves through careful analysis of ring structure. The irony persists that this cosmic pygmy among moons exerts more influence on Saturn's rings than objects many times its size, simply by virtue of occupying the right orbital distance to create strong, resonant relationships. The discovery of the Cassini division's resonant origin revolutionized understanding of planetary ring dynamics and demonstrated that apparently empty regions of space can be as dynamically significant as regions filled with matter. The division serves as a natural laboratory for studying how gravitational resonances operate in multi-body systems, providing insights that apply to phenomena ranging from asteroid belt structure to the orbital architecture of exoplanetary systems. The mathematical relationships that govern the division's existence remain as pure and eternal as any theorem in geometry, yet manifest themselves through the physical reality of countless ice particles following the inexorable laws of orbital mechanics. Modern computer simulations reveal that the Cassini division's structure represents a delicate balance between creation and destruction processes that operate on vastly different timescales. While the resonant clearing mechanism removes particles over periods of thousands to millions of years, other processes continuously supply new material to the region through meteoroid impacts on nearby ring particles, erosion from electromagnetic effects, and gravitational perturbations that scatter particles from adjacent ring regions. The division's current appearance thus represents a dynamic equilibrium between these competing processes, maintained by the mathematical certainty of orbital resonances, yet subject to slow evolution as the entire Saturn system ages. Perhaps the division itself experiences seasons of fullness and emptiness that span geological ages, cycling through states of matter and void according to rhythms too slow for human minds to comprehend directly. Above the mathematical precision of Saturn's ring plane, electromagnetic forces lift microscopic particles into temporary freedom from their ordained orbital paths, creating ghostly structures that appear and vanish like the spokes of an invisible wheel turning in slow motion against the cosmic dark. These ring spokes, first observed by Voyager spacecraft in the early 1980s, emerge from the ring material as dark radial features that extend from the inner edge of the B ring outward across tens of thousands of kilometers, rotating with Saturn's magnetic field rather than following the orbital mechanics that govern larger ring particles. The spokes form when Saturn's rotating magnetic field generates electrostatic charges on the smallest ring particles, dust grains measuring only micrometers across. Smaller than the particles in cigarette smoke, yet suspended in the vacuum of space through forces that operate on scales invisible to direct observation. These charged dust grains experience electromagnetic forces that can overcome Saturn's gravity for brief periods, lifting them above and below the ring plane in patterns that follow the planet's 10-hour rotation period rather than the orbital periods of ring material, which range from 7 to 14 hours depending on distance from Saturn. The electromagnetic environment that creates ring spokes operates through mechanisms that remain partially mysterious despite decades of study. Saturn's magnetic field, generated by electrical currents flowing within the planet's metallic hydrogen core, threads through the ring system and drags charged particles along magnetic field lines that co-rotate with the planet's interior. When these field lines intersect with ring material, they can transfer charge to dust particles through contact electrification, the same process that creates static electricity when you rub a balloon against your hair, but operating on a scale that spans hundreds of thousands of kilometers and involves billions of microscopic interactions per second. The formation of a single spoke begins with what scientists call an electrostatic discharge event, essentially a lightning strike within the ring system that charges dust particles in a localized region. These newly charged particles then respond to Saturn's magnetic field and lift away from the ring plane, creating a dark shadow against the brighter background of uncharged ring material. The entire process occurs within minutes, yet the resulting spoke structure can persist for hours as it rotates around Saturn, gradually dispersing as the charged particles either lose their charge through collisions or drift away from their initial formation region. Telescopic observations from Earth reveal that spoke activity varies with Saturn's seasons, becoming more prominent when the ring plane faces directly toward or away from the sun, and nearly disappearing when the rings are edge-on to solar illumination. This seasonal variation suggests that solar ultraviolet radiation plays a crucial role in the spoke formation process, perhaps by enhancing the charging of dust particles or by affecting the electrical properties of ring material itself. The spokes thus represent a form of space weather operating within Saturn's ring system, driven by the complex interaction between solar radiation, planetary magnetic fields, and the microscopic dust that fills the space between larger ring particles. The physics governing spoke behavior differs fundamentally from the gravitational dynamics that control larger ring structures. While kilometer-sized ring particles follow predictable elliptical orbits determined by Saturn's mass and distance, micrometer-sized dust grains experience forces that can accelerate them to speeds of several kilometers per second, fast enough to escape Saturn's gravitational influence entirely if the electromagnetic forces persist long enough. Most charged dust particles return to the ring plane within a few hours as they lose their charge or as magnetic field variations cause them to follow complex spiral paths back toward their original orbital zones. Computer simulations of spoke dynamics reveal structures of extraordinary complexity hidden within these apparently simple radial features. Individual spokes contain millions of charged dust particles following independent trajectories through three-dimensional space, their paths determined by the constantly changing balance between electromagnetic forces, Saturn's gravity, and interactions with neutral ring material. The resulting particle motions create temporary density variations that can be detected through their effects on radio waves transmitted through the ring system, revealing spoke structure at resolutions impossible to achieve through optical observations alone. The electromagnetic forces that create ring spokes operate on energy scales that dwarf human technology, yet remain barely detectable against the gravitational forces that dominate ring dynamics. A typical spoke formation event releases energy equivalent to several lightning bolts, but spread across a region larger than most countries and distributed among particles so small that billions of them could fit within a single raindrop. This energy comes from Saturn's rotation, which maintains the magnetic field that drives spoke formation, making the spokes a visible manifestation of the planet's internal dynamics projected onto the ring system like shadows cast by invisible electromagnetic machinery. The temporal behavior of ring spokes follows patterns that suggest deep connections to Saturn's internal structure and atmospheric dynamics. Spoke activity shows correlations with Saturn's radio emissions, which originate from charged particle interactions in the planet's magnetosphere, and with the intensity of Saturn's kilometric radiation, electromagnetic signals generated by the same magnetic field processes that create aurora on Earth. These correlations imply that ring spokes represent just one component of a larger electromagnetic system that links Saturn's interior, magnetosphere, and ring environment in ways that remain incompletely understood. Modern infrared observations reveal that spoke particles have different temperatures than the surrounding ring material, remaining slightly warmer due to their smaller size and enhanced absorption of solar radiation. This temperature difference creates thermal emission signatures that allow astronomers to track spoke evolution even when the structures are too faint for optical detection. The spokes thus live double lives as both visible phenomena and thermal anomalies, existing simultaneously in multiple wavelengths of electromagnetic radiation that each reveal different aspects of their complex physical nature. Only a cosmic accident could have created conditions where planetary magnetism, solar radiation, and ring dynamics combine to produce ephemeral structures that appear solid to distant observers, yet consist of nothing more than temporarily organized clouds of electrostatically charged cosmic dust. Hidden within Saturn's vast ring system, objects the size of city blocks carve wakes through the surrounding ice particles, their presence revealed not through direct observation, but through the subtle gravitational disturbances they create in the cosmic debris field around them. These moonlets, measuring between 1 and 20 kilometers across, exist embedded within the ring plane itself. Too small for telescopes to resolve directly, yet massive enough to create characteristic propeller-shaped patterns in the ring material that stretches for hundreds of kilometers on either side of their invisible forms. The propeller structures form through a delicate balance between the moonlet's gravitational influence and the natural orbital dynamics of ring particles. As a moonlet moves through the ring plane, its gravity attracts nearby particles, accelerating those that approach from behind and decelerating those that approach from ahead, the same shepherding mechanism that operates around larger moons but scaled down to objects barely larger than mountains. The result creates zones of enhanced and depleted particle density that follow the moonlet's orbital path like a ship's wake, except these wakes persist for thousands of kilometers and remain stable for years or decades. Computer simulations reveal the intricate physics governing propeller formation with mathematical precision that would satisfy the most demanding celestial mechanician. Ring particles approaching a moonlet from its trailing edge gain orbital energy from the gravitational encounter, causing them to move into slightly higher, slower orbits that create a region of enhanced density behind the moonlet. Particles approaching from the leading edge lose orbital energy and fall into lower, faster orbits, creating a depleted zone ahead of the moonlet's position. These density variations propagate outward from the moonlet's orbit, creating the characteristic asymmetric pattern that gives propeller structures their distinctive appearance. The discovery of propeller moonlets revolutionized understanding of ring evolution by revealing processes that operate on intermediate scales between individual particle collisions and the large-scale gravitational resonances that shape major ring features. Unlike the shepherd moons that orbit outside the ring system, propeller moonlets exist within the ring environment itself, experiencing constant bombardment by smaller particles while simultaneously influencing the orbital dynamics of material across regions spanning hundreds of kilometers. This bombardment gradually erodes the moonlets over geological time, yet also provides a mechanism for their growth if they can accrete material faster than they lose it to impacts. Observations from the Cassini spacecraft identified more than 100 propeller structures within Saturn's A-ring, each one marking the location of an embedded moonlet whose gravitational influence extends far beyond its physical size. The largest propellers, nicknamed Blériot, Earhart, and Santos Dumont after aviation pioneers, create disturbances visible across distances of 3,000 kilometers or more, suggesting moonlets with diameters approaching 20 kilometers, objects large enough to have significant geological structure, yet small enough to remain gravitationally bound to the ring system rather than clearing gaps like larger moons. The orbital evolution of propeller moonlets demonstrates principles of celestial mechanics that apply throughout the solar system, from asteroid belt dynamics to the formation of planetary systems around other stars. Each moonlet follows a slowly evolving elliptical orbit that changes over time due to gravitational interactions with ring particles, causing the associated propeller structure to shift position and orientation within the ring plane. Some propellers show systematic changes in their appearance over periods of years, suggesting that their central moonlets experience orbital migration at rates of several kilometers per year, fast enough to measure with careful observations, yet slow enough that the propeller structures can adapt to their moonlets' changing positions. The size distribution of propeller moonlets follows mathematical patterns that provide clues about the processes responsible for their formation and evolution. Smaller propellers vastly outnumber larger ones, following a power law relationship that suggests these objects formed through collisional fragmentation of larger bodies rather than through gradual accretion of ring material. This size distribution implies that Saturn's rings once contained much larger embedded objects that were broken apart by catastrophic impacts, leaving behind a population of moonlet fragments that continue to evolve through ongoing collisional processes operating on timescales of millions to hundreds of millions of years. The material composition of propeller moonlets remains largely unknown since they cannot be observed directly, but their gravitational effects on surrounding ring particles provide indirect constraints on their properties. The strength of propeller disturbances suggests bulk densities similar to water ice with some rocky contamination compositions consistent with the ring particles themselves and with the icy moons that populate the outer solar system. Some propellers show variations in their disturbance patterns that might indicate irregular shapes or internal density variations, suggesting that these moonlets represent gravitationally bound rubble piles rather than solid objects. The electromagnetic environment surrounding propeller moonlets adds another layer of complexity to their dynamics. Like all objects within Saturn's ring system, the moonlets exist within the planet's rotating magnetic field and may acquire electrostatic charges through impacts with charged ring particles or through direct interaction with the plasma environment. These electromagnetic effects could influence the moonlet's ability to accrete or shed material, potentially affecting their long-term evolution in ways that remain poorly understood. The moonlets thus represent natural laboratories for studying how electromagnetic forces interact with gravitational dynamics in environments that have no analog within terrestrial experience. The long-term fate of propeller moonlets depends on the balance between growth through accretion and destruction through impacts and electromagnetic erosion. Computer models suggest that most embedded moonlets will eventually be destroyed by collisions with other ring material or by tidal disruption if their orbits evolve to bring them too close to Saturn itself. Yet the presence of so many propellers in Saturn's current ring system suggests either that the moonlets formed relatively recently, or that processes exist to continuously create new moonlets from the breakup of larger objects. Only the rings themselves know whether the propeller population represents the dying remnants of ancient embedded moons or the growing seeds of future satellite systems. Their gravitational signatures encoding the history and destiny of an entire cosmic ecosystem in patterns visible only through the patient analysis of subtle disturbances in streams of orbiting ice. In one of the most startling discoveries of modern planetary science, Saturn's magnificent ring system, often considered the most ancient and enduring feature of the outer solar system, appears to be younger than the dinosaurs that once walked Earth's continents. Radiometric dating techniques applied to data from the Cassini spacecraft suggest the rings formed between 100 and 400 million years ago, during the Devonian or Carboniferous periods when terrestrial life was first colonizing dry land and vast forests were laying down the coal deposits that would power human civilization billions of years later. This surprisingly recent age emerges from careful analysis of the rings' chemical composition and the rate at which they accumulate contamination from interplanetary dust and meteoroid impacts. Saturn's rings consist of nearly pure water ice, cleaner than any natural ice found on Earth, with less than 5% rocky material mixed throughout the system. This purity represents a cosmic puzzle, because ring particles should gradually darken as they accumulate debris from the constant rain of meteoroids that falls throughout the solar system. A contamination process that operates like geological erosion, but in reverse, adding material rather than removing it. Computer models tracking this contamination process reveal that ring particles should accumulate rocky material at a rate determined by the flux of interplanetary debris, the impact velocities of meteoroids striking ring particles, and the efficiency with which impact ejecta escapes versus remains bound to the ring system. These calculations suggest that rings formed during the early solar system, 6 billion years ago, would now contain at least 20 to 30% rocky contamination, far more than the pristine ice composition actually observed. The rings' current purity thus provides a cosmic clock that limits their maximum age to a few 100 million years at most. The implications of this youthful age challenge fundamental assumptions about planetary system evolution and the stability of ring structures around giant planets. For decades, astronomers assumed Saturn's rings represented primordial material left over from the planet's formation, preserved in pristine condition by the vacuum of space and the mathematical precision of orbital mechanics. Instead, the rings appear to represent a recent catastrophic event in Saturn's history, perhaps the tidal disruption of a large icy moon that wandered too close to the planet, or the collision between two of Saturn's satellites that scattered debris throughout the inner satellite system. The tidal disruption scenario offers the most plausible mechanism for creating rings with the observed mass and composition. When an icy moon approaches within Saturn's roche, limit the distance at which tidal forces overcome the object's self-gravity, it stretches and fragments into a stream of debris that gradually spreads into a thin, disc-like configuration. Computer simulations of this process show that disruption of a moon roughly the size of Mimas could produce rings with properties matching Saturn's current system, including the total mass, chemical composition, and basic architectural features such as the major gaps and divisions. The collision scenario presents an alternative pathway that could also explain the ring's youthful appearance and chemical purity. If two of Saturn's icy moons collided at velocities of several kilometers per second, the impact would vaporize much of both objects while creating a debris cloud composed primarily of water ice with minimal rocky contamination. The collision debris would then evolve under gravitational and electromagnetic forces to form the ring structures observed today, preserving chemical signatures from the original impact event while developing the complex dynamics that characterize modern ring behavior. Either formation mechanism implies that Saturn's ring system represents a temporary feature in the planet's evolution, a cosmic accident that created one of the solar system's most spectacular sights through the destruction of pre-existing moons. This perspective transforms understanding of ring dynamics from the study of ancient, stable structures to the investigation of actively evolving debris systems that may disappear entirely within another few 100 million years as ring particles gradually spiral inward towards Saturn or disperse outward into the satellite system. The recent formation of Saturn's rings also explains several puzzling aspects of their current structure and dynamics. Young rings would still retain memory of their catastrophic origin through features such as the complex spoke patterns in the B ring, the braided structure of the F ring, and the numerous embedded moonlets that create propeller disturbances throughout the A ring. These features represent a transitional phenomena, remnants of the violent processes that created the rings, gradually evolving towards simpler configurations as the system ages and the effects of its traumatic birth fade into mathematical regularity. Chemical analysis of ring particles provides additional evidence for recent formation through catastrophic disruption of icy satellites. Spectroscopic observations reveal trace amounts of organic compounds coating some ring particles, complex hydrocarbons similar to those found on Saturn's moon Titan and other icy bodies throughout the outer solar system. These organic materials would be destroyed by solar ultraviolet radiation over periods of tens to hundreds of millions of years. Yet their presence in the rings suggests either very recent formation or ongoing replenishment from sources that remain active today. The discovery of Saturn's rings' youthful age raises profound questions about the frequency and timing of catastrophic events in mature planetary systems. If such dramatic restructuring can occur hundreds of millions of years after initial system formation, other planets may have experienced similar episodes of satellite destruction and ring creation throughout solar system history. Earth's moon bears scars from the late heavy bombardment that occurred 3.8 billion years ago, but perhaps more recent catastrophes have reshaped satellite systems around the giant planets, creating and destroying ring systems in cycles that span hundreds of millions of years. Modern observations of exoplanetary systems provide tantalizing hints that ring formation may represent a common phase in planetary evolution rather than a rare cosmic accident. Transit observations of young exoplanets occasionally show evidence for circumplanetary material that could represent ring systems, though the extreme distances involved make detailed characterization impossible with current technology. Saturn's rings thus serve as a natural laboratory for understanding processes that may operate throughout the galaxy, transforming satellite systems through catastrophic events that reshape entire planetary environments within geological eye blinks. Only the universe could create beauty this spectacular through destruction this complete, leaving behind mathematical perfection forged in the crucible of cosmic violence that occurred while trilobites still dominated Earth's ancient seas. Within Saturn's ring system, the memory of ancient collisions persists as traveling waves that propagate outward from their points of origin like ripples in a cosmic pond, carrying the signatures of impacts that occurred decades ago across distances spanning thousands of kilometers. These vertical waves, first detected through careful analysis of stellar occultation data, manifest as periodic variations in ring particle height that cause portions of the ring plane to oscillate up and down with mathematical precision, creating three-dimensional structures within what appears from a distance to be a perfectly flat disk of ice and debris. The waves originate when large meteoroids, chunks of rock and ice measuring meters to tens of meters across, strike the ring plane at high velocity, creating impact sites that disturb the normally planar distribution of ring material. The collision itself lasts only seconds, but its gravitational effects propagate outward at speeds determined by the local orbital dynamics and the ring's internal structure, creating disturbances that can remain detectable for years or decades after the original impact event. Each wave represents a fossilized record of cosmic violence, preserved in the collective motion of millions of ring particles that continue to bob up and down in response to gravitational echoes from impacts they never experienced directly. Computer simulations reveal the intricate physics governing wave propagation through Saturn's rings with a precision that rivals studies of seismic waves traveling through Earth's interior. When a meteoroid strikes ring material, it creates a localized compression that increases particle density and disturbs the gravitational field within the impact region. This disturbance propagates outward as a spiral density wave that follows mathematical patterns determined by the ring's rotation rate, the local gravitational environment, and the efficiency with which ring particles can transmit momentum through gentle collisions with their neighbors. The vertical component of these impact waves emerges from the three-dimensional nature of ring particle orbits, which can be tilted slightly with respect to the average ring plane. When a wave passes through a region, it temporarily alters the orbital inclinations of affected particles, causing them to bob above and below their normal positions in a coordinated pattern that travels outward from the impact site like a slow-motion version of stadium waves created by cheering crowds. The entire process operates through gravitational forces so subtle that individual ring particles remain unaware of their participation in structures that span distances comparable to Earth's diameter. Stellar occultation observations provide the primary method for detecting and studying these vertical waves, as distant stars appear to twinkle when viewed through ring material whose vertical structure varies periodically. The timing and amplitude of these brightness variations encode information about wave properties with such precision that astronomers can reconstruct the original impact events that created them, determining not only when and where meteoroids struck the rings, but also their approximate sizes and impact velocities. The rings thus serve as a vast natural seismograph that records the bombardment history of the Saturn system with temporal resolution measured in years and spatial resolution measured in kilometers. The most prominent impact waves detected in Saturn's rings can be traced to specific meteoroid impacts that occurred during the 1980s and 1990s, coinciding with the breakup of Comet Shoemaker-Levy 9 and other disruption events that increased the flux of large debris throughout the outer solar system. These waves appear as spiral patterns that wind outward through the ring plane, their wavelengths and propagation speeds determined by the local gravitational environment and the physical properties of ring material itself. The waves demonstrate that Saturn's rings respond to external perturbations as a coherent dynamical system, with disturbances in one region affecting particle motions across the entire ring structure through mechanisms that operate over geological timescales. The mathematical description of impact wave propagation requires sophisticated theories that combine celestial mechanics, fluid dynamics, and statistical mechanics to account for the complex interactions between billions of individual ring particles. Each particle follows its own elliptical orbit around Saturn while simultaneously participating in collective behaviors that emerge from gravitational interactions with its neighbors. The resulting dynamics create phenomena that have no terrestrial analog waves that travel through a medium composed of discrete objects orbiting in vacuum, maintained by gravitational forces alone, yet exhibiting properties reminiscent of sound waves traveling through continuous media. The long-term evolution of impact waves reveals fundamental properties of ring material that cannot be measured through any other observational technique. Wave damping rates provide information about the efficiency of inelastic collisions between ring particles, while wave dispersion characteristics reveal how gravitational forces propagate through the ring system at different spatial scales. These measurements suggest that ring particles behave more like a granular fluid than either a solid or a conventional gas, exhibiting collective properties that emerge from the statistical behavior of countless individual orbits rather than from direct mechanical coupling between particles. Some impact waves show evidence for interactions with existing ring structures, creating interference patterns where multiple waves overlap or reflecting from density variations created by gravitational resonances with Saturn's moons. These interactions can amplify or cancel wave features, creating complex patterns that evolve over time as different wave components propagate at different speeds through the varying gravitational environment of the ring system. The resulting structures demonstrate that Saturn's rings support a rich variety of wave phenomena that continue to be discovered through increasingly sophisticated analysis techniques applied to decades of accumulated observational data. The detection of impact waves has practical implications for understanding the current bombardment rate in the outer solar system and the hazards posed by large meteoroids to spacecraft operating in planetary ring environments. The frequency and intensity of wave-generating impacts provide direct measurements of the flux of debris larger than a few meters across, objects too small for ground-based telescopes to detect directly, yet large enough to pose significant risks to future robotic missions. The rings thus serve as natural impact detectors that monitor cosmic debris on spatial and temporal scales impossible to achieve through conventional surveillance methods. Modern theoretical models suggest that impact waves may play important roles in the long-term evolution of planetary ring systems by transporting angular momentum and energy across large distances, potentially affecting the rates at which rings spread outward or spiral inward toward their parent planets. The waves represent mechanisms for coupling local disturbances to global ring dynamics, creating feedback systems that could influence ring stability and longevity over geological timescales. Perhaps the rings themselves remember every significant impact through wave patterns that persist like scars in their gravitational memory, encoding the bombardment history of the entire Saturn system in oscillations too subtle for casual observation, yet detectable through the patient analysis of starlight filtered through cosmic ice. Only the universe could design a record-keeping system where the echoes of ancient collisions continue to ripple through space, decades after the original impacts faded into silence. Across the vast expanse of Saturn's ring system, temperature variations create a thermal landscape as complex and dynamic as weather patterns on planetary surfaces. Yet operating in the profound cold of interplanetary space, where the warmest regions barely reach temperatures that would instantly freeze any terrestrial substance. Ring particles experience temperature swings that span 60 degrees Celsius as they rotate through alternating periods of sunlight and shadow, their surfaces expanding and contracting in the vacuum like frozen heartbeats that pulse with the rhythm of Saturn's 10-hour day. In the deepest shadows cast by Saturn's bulk, ring particles cool to temperatures approaching -200 degrees Celsius, so cold that nitrogen would freeze solid and carbon dioxide would behave like granite. These shadowed regions exist as thermal oases of absolute stillness, where molecular motion nearly ceases and the quantum mechanical properties of matter begin to dominate classical physics. Yet, within minutes, orbital motion carries these same particles back into direct sunlight, where temperatures climb to merely -120 degrees Celsius, warming them enough to sublimate trace amounts of water, ice directly into vapor that immediately refreezes on adjacent particles or escapes entirely into the vacuum of space. The thermal dynamics governing ring particle temperatures operate through radiation processes that follow the fundamental laws of blackbody physics, yet create patterns of complexity that emerge from the three-dimensional architecture of the ring system itself. Particles in the dense B ring experience different thermal environments than those in the sparse outer regions, not only because of their varying distances from Saturn, but also because of the thermal radiation they exchange with neighboring particles. Dense ring regions act like cosmic greenhouses where particles radiatively heat each other, maintaining temperatures several degrees warmer than isolated particles would achieve at the same distance from the Sun. Computer models of ring thermal dynamics reveal that individual particles experience temperature cycles more complex than simple heating and cooling based on solar illumination. Large particles, measuring meters across, develop temperature gradients between their sunlit and shadowed hemispheres that persist for hours as thermal energy slowly conducts through their icy interiors. Smaller particles, ranging from centimeters to millimeters in size, achieve thermal equilibrium within minutes, but experience more extreme temperature swings because their low thermal mass cannot buffer against rapid changes in their radiative environment. The thermal properties of ring material itself remain largely mysterious despite decades of infrared observations from spacecraft and ground-based telescopes. Ring particles appear to consist of nearly pure water ice with thermal conductivities and heat capacities that depend sensitively on the presence of trace contaminants, internal porosity, and surface texture. Fresh ice surfaces reflect solar radiation efficiently, maintaining lower temperatures than particles contaminated with dark organic compounds or rocky debris. The thermal behavior of ring particles thus provides clues about their composition and evolutionary history, encoded in temperature variations measurable to precision of a few degrees across distances spanning hundreds of thousands of kilometers. Infrared spectroscopy reveals thermal emission from ring particles that varies systematically with position within the ring system, creating temperature maps that show the thermal signatures of major ring features and dynamic processes. The Cassini division appears cooler than adjacent ring regions because its sparse particle population cannot maintain the thermal coupling that warms denser areas. Density waves and spiral structures create thermal patterns that propagate through the ring system as variations in particle spacing alter the efficiency of radiative heat transfer between neighboring objects. The seasonal thermal cycle of Saturn's ring system operates on timescales that dwarf human experience, as the planet's 29.5-year orbital period around the Sun creates climate changes that unfold over decades. During Saturn's northern summer, the ring plane tilts toward the Sun at its maximum angle, exposing both sides of the rings to direct solar heating for the first time in nearly 15 years. This enhanced illumination increases ring temperatures by 10 to 20 degrees Celsius, changes large enough to alter the sublimation rates of water ice and potentially affect the dynamics of charged dust particles that create ring spokes and other electromagnetic phenomena. The thermal infrared emission from Saturn's rings provides one of the few direct methods for measuring the sizes of ring particles, as objects of different sizes cool at different rates after emerging from Saturn's shadow. Large particles retain heat longer than small ones, creating thermal inertia signatures that can be detected through careful timing of infrared observations. These thermal measurements suggest that most ring particles range from centimeters to meters in diameter, with size distributions that vary systematically across different regions of the ring system according to patterns that reflect the balance between collisional fragmentation and gravitational aggregation operating over geological timescales. The interaction between thermal processes and ring dynamics creates feedback mechanisms that influence the long-term evolution of the entire system. Temperature variations affect the efficiency of inelastic collisions between ring particles, as colder particles tend to stick together more readily when they impact at low velocities. Thermal cycling may also contribute to the gradual fragmentation of larger particles through repeated expansion and contraction that creates internal stresses in ice structures already weakened by previous collisions or radiation damage from energetic charged particles in Saturn's magnetosphere. Sublimation of water ice from ring particle surfaces represents a continuous mass loss process that operates at rates determined by local temperature and the extremely low vapor pressure environment of interplanetary space. Even at the frigid temperatures typical of Saturn's rings, water molecules occasionally acquire enough thermal energy to escape directly from ice surfaces into the surrounding vacuum, creating tenuous atmospheres around individual particles that immediately disperse into space. This sublimation process may contribute to the erosion of ring particles over geological time, gradually removing mass from the system and contributing to the formation of Saturn's tenuous hydroxyl cloud that extends throughout the inner magnetosphere. The thermal environment of Saturn's rings also influences electromagnetic phenomena such as spoke formation and the charging of dust particles that occurs through contact with Saturn's rotating magnetic field. Temperature affects the electrical conductivity of ice surfaces and the efficiency with which particles can acquire and retain electrostatic charges. Warmer particles may be more susceptible to electromagnetic forces that lift them out of the ring plane, while colder particles might remain more tightly bound to their prescribed orbital paths. The thermal landscape of the rings thus interacts with electromagnetic processes in ways that remain incompletely understood, creating coupled thermal electromagnetic dynamics that operate across spatial scales ranging from individual particle surfaces to the entire ring system. Modern infrared observations from space-based telescopes continue to reveal new aspects of ring thermal behavior, including evidence for temperature variations that correlate with the orbital phases of shepherd moons, density waves generated by gravitational resonances, and even the passage of impact-generated waves that create temporary thermal anomalies as they propagate through ring material. These thermal signatures provide complementary information to optical and radio observations, revealing aspects of ring structure and dynamics that remain invisible at other wavelengths. Perhaps the rings themselves experience thermal weather systems that create patterns of warmth and cold as ephemeral as clouds, yet as mathematically precise as the orbital mechanics that govern their existence, encoding the history of solar heating and electromagnetic interaction in temperature variations that persist like thermal memories frozen into the cosmic architecture of ice and shadow. High above Saturn's North Pole, a geometric marvel defies conventional understanding of atmospheric dynamics, a hexagonal cloud pattern that maintains its six-sided symmetry with mathematical precision across decades of observation, its edges as straight as if drawn with cosmic rulers, and its vertices as sharp as crystalline formations carved by celestial geometry. This hexagonal storm system, measuring 30,000 kilometers across and large enough to contain 4 Earth-sized planets within its boundaries, rotates as a single coherent structure with a period of 10 hours and 39 minutes, creating one of the most enigmatic and visually striking features in the entire solar system. The hexagon's influence extends far beyond Saturn's upper atmosphere, reaching down through the planet's complex magnetic field to subtly affect the electromagnetic environment that permeates the ring system below. Saturn's magnetic field, generated by electrical currents flowing within the planet's metallic hydrogen core, follows field lines that thread through both the atmospheric hexagon and the ring plane, creating pathways for electromagnetic energy to propagate between these seemingly disconnected regions of the Saturn system. The hexagon thus serves as a high-altitude electromagnetic beacon whose effects may influence ring dynamics through mechanisms that operate on timescales ranging from hours to decades. Computer simulations of Saturn's magnetosphere reveal how atmospheric phenomena at the planet's poles can affect charged particle populations throughout the inner satellite system, including the region occupied by the rings. The hexagon's rotation creates periodic variations in the magnetic field configuration above Saturn's North Pole, generating electromagnetic waves that propagate along magnetic field lines at velocities approaching the speed of light. These waves can accelerate charged particles within Saturn's radiation belts, potentially affecting the formation of ring spokes and other electromagnetic phenomena that depend on the interaction between charged dust and magnetic fields. The hexagon's geometric perfection emerges from atmospheric dynamics that involve standing wave patterns in Saturn's upper atmosphere, where jet streams flowing at different latitudes create interference patterns that lock into stable six-sided configurations. This atmospheric hexagon demonstrates how non-linear fluid dynamics can spontaneously organize into regular geometric forms, providing insights into pattern formation processes that may operate throughout nature. The hexagon's persistence over multiple decades suggests that Saturn's atmospheric circulation maintains remarkable stability despite the complex three-dimensional flows that characterize giant planet weather systems. Spectroscopic observations of the hexagon reveal trace amounts of organic compounds and hydrocarbons that form through photochemical reactions driven by solar ultraviolet radiation interacting with Saturn's upper atmosphere. These same chemical species appear in much smaller concentrations throughout Saturn's magnetosphere, including regions that encompass the ring system. The hexagon may thus serve as a source of organic molecules that gradually diffuse throughout the Saturn system, potentially contributing to the trace organic compounds detected on ring particle surfaces through processes that operate over timescales of millions to hundreds of millions of years. The electromagnetic coupling between Saturn's hexagon and ring system operates through phenomena that have no terrestrial analog, involving the complex interaction between atmospheric circulation patterns, planetary magnetic fields, and charged particle dynamics in ways that remain incompletely understood despite decades of theoretical investigation. The hexagon's influence on ring electromagnetic phenomena may manifest through variations in the intensity and spatial distribution of charged particle precipitation into the ring plane, affecting the formation of spokes, the charging of dust particles, and the electromagnetic erosion of ring material over geological timescales. Thermal infrared observations of the hexagon reveal temperature variations that create convection patterns extending deep into Saturn's atmosphere, potentially affecting the generation of the planet's magnetic field through magnetohydrodynamic processes operating within the metallic hydrogen region thousands of kilometers below the visible cloud tops. These deep atmospheric circulation patterns may create temporal variations in Saturn's magnetic field, strength, and configuration, subtly affecting the electromagnetic environment experienced by ring particles and the efficiency of processes such as spoke formation and charged particle transport throughout the ring system. The hexagon's role in Saturn's global energy budget remains an active area of research, as this massive atmospheric feature represents a significant reservoir of kinetic and thermal energy that exchanges heat and momentum with other components of Saturn's atmospheric circulation. The hexagon's stability suggests that it participates in energy balance processes that help maintain Saturn's overall atmospheric structure, potentially influencing the planet's thermal emission patterns and the efficiency with which internal heat reaches the upper atmosphere where it can be radiated away to space. Modern theoretical models suggest that the hexagon may represent just one component of a larger pattern of atmospheric magnetospheric coupling that operates throughout the Saturn system, linking atmospheric dynamics, magnetic field generation, and ring electromagnetic phenomena through complex feedback mechanisms that operate on multiple timescales. The hexagon's influence on ring dynamics may be most pronounced during periods of enhanced atmospheric activity, when increased storm formation and jet stream variations create stronger electromagnetic disturbances that propagate through the magnetosphere to affect charged particle populations within the ring environment. The discovery of similar hexagonal patterns in laboratory experiments involving rotating fluids provides insights into the physical mechanisms responsible for the Saturn hexagon's formation and stability, suggesting that this phenomenon represents a fundamental manifestation of fluid dynamics under conditions of rapid rotation and strong temperature gradients. These laboratory studies reveal that hexagonal flow patterns can emerge spontaneously from initially chaotic fluid motions, achieving stable configurations that persist indefinitely under appropriate boundary conditions, a process that may help explain how Saturn's hexagon maintains its geometric perfection across decades of observation. The long-term evolution of Saturn's hexagon and its influence on ring dynamics may be connected to seasonal changes in Saturn's atmospheric circulation that occur as the planet completes its 29.5-year orbit around the Sun. During Saturn's northern summer, enhanced solar heating of the hexagon region may strengthen atmospheric circulation patterns and increase the intensity of electromagnetic coupling to the ring system, potentially affecting spoke formation rates and other electromagnetic phenomena that vary with Saturn's seasons. The hexagon thus represents a high-altitude window into atmospheric processes that may influence ring dynamics through pathways that connect Saturn's deepest interior to the cosmic vacuum where ring particles orbit in mathematical precision. The geometric perfection of Saturn's hexagon serves as a constant reminder that nature can spontaneously organize into patterns of extraordinary regularity and beauty through the operation of fundamental physical laws acting on cosmic scales. The hexagon's influence on ring electromagnetic phenomena demonstrates how atmospheric dynamics on one world can affect the behavior of orbiting debris through electromagnetic pathways that span thousands of kilometers, yet operate with the precision of atomic interactions. Perhaps the hexagon itself represents a form of planetary consciousness, a geometric thought pattern traced in atmospheric circulation that influences the electromagnetic dreams of ring particles orbiting in the cosmic darkness below, their charged dust dancing to rhythms established by six-sided atmospheric symphonies that play on timescales measured in decades, yet maintain their geometric harmony with the persistence of mathematical truth. Within the crystalline ice that composes Saturn's ring particles, organic molecules hide in concentrations so minute they could pass unnoticed for eons, Yet their presence transforms these frozen fragments into chemical archives that preserve signatures from the earliest epochs of solar system formation. These complex hydrocarbons, compounds containing chains and rings of carbon atoms decorated with hydrogen and other elements, coat ring particle surfaces in layers only molecules thick, creating chemical fingerprints that reveal connections between Saturn's rings and the primordial disk of gas and dust from which all planets condensed 4.6 billion years ago. The organic compounds detected on ring particles include molecules as simple as methane and as complex as polycyclic aromatic hydrocarbons, carbon-rich structures that form through high-temperature chemical processes, operating in environments ranging from stellar atmospheres to the interiors of meteorites. These same molecular families appear throughout the outer solar system, from the hydrocarbon lakes of Titan to the organic-rich surfaces of Kuiper Belt objects, suggesting that ring particles preserve chemical information from the vast reservoir of organic material that once filled the outer regions of the developing solar system. Spectroscopic analysis reveals that organic molecules concentrate preferentially on ring particle surfaces rather than being distributed uniformly throughout their icy interiors, indicating that these compounds arrived through external processes rather than forming within the ice itself. The surface concentration of organics suggests deposition through mechanisms such as ion bombardment from Saturn's magnetosphere, accretion of organic-rich micrometeorites, or chemical processing of simple carbon-bearing molecules under the influence of solar ultraviolet radiation and charged particle interactions that operate continuously throughout the ring environment. The chemical composition of ring particle organics provides clues about the thermal and radiation environment experienced by these materials throughout their history. Some organic molecules show evidence for thermal processing that occurs when ice particles experience heating during energetic collisions or electromagnetic interactions, while others preserve signatures of cold formation processes that operated in the low-temperature conditions typical of the outer solar system. The coexistence of thermally processed and pristine organic molecules on ring particle surfaces suggests that these materials have experienced complex chemical evolution over geological timescales. Computer models of organic molecule formation and destruction in planetary ring environments reveal the delicate balance between creation and destruction processes that determines the steady-state concentrations observed on ring particles. Solar ultraviolet radiation continuously breaks down complex organic molecules into simpler fragments, while charged particle bombardment from Saturn's magnetosphere can both destroy existing organics and synthesize new compounds through radiation chemistry. The observed organic concentrations thus represent equilibrium between these competing processes, maintained over timescales ranging from thousands to millions of years. The discovery of organic molecules on ring particles has profound implications for understanding the chemical evolution of icy bodies throughout the solar system and the potential for prebiotic chemistry in environments far from the traditional habitable zones around stars. While Saturn's rings remain far too cold and radiation-rich to support life as we know it, the presence of complex organics demonstrates that carbon-based chemistry can operate and persist in extreme environments where only mathematical precision governs the motion of matter through vacuum and electromagnetic fields. The spatial distribution of organic molecules throughout Saturn's ring system shows systematic variations that correlate with ring density, particle size distributions, and electromagnetic field strength. The dense B ring contains higher concentrations of organics than the sparse outer regions, possibly due to enhanced shielding from destructive solar radiation or more efficient retention of organic-rich micrometeorites through gravitational focusing effects. These spatial variations suggest that organic chemistry in planetary ring systems depends sensitively on local physical conditions that affect both the supply and destruction rates of carbon-bearing molecules. Theoretical calculations indicate that some organic molecules detected on ring particles may originate from Titan, Saturn's largest moon, through complex pathways involving atmospheric escape, electromagnetic transport, and subsequent capture by ring material. Titan's thick nitrogen-methane atmosphere continuously produces organic compounds through photochemical reactions, and some of this material escapes to space where it can be transported throughout the Saturn system by magnetic field interactions and solar wind effects. The rings may thus serve as repositories for organic molecules that chronicle the chemical evolution of Titan's atmosphere over geological time. The isotopic signatures of organic molecules on ring particles provide additional constraints on their formation mechanisms and evolutionary history. Different isotopic ratios of carbon, nitrogen, and other elements reflect the temperature and pressure conditions under which organic molecules formed, as well as the degree of subsequent processing through radiation and thermal effects. These isotopic fingerprints suggest that ring particle organics derive from multiple sources and formation pathways, creating chemical diversity that rivals the complexity found in meteorites and cometary materials. The long-term stability of organic molecules in Saturn's ring environment depends on the balance between protective and destructive factors operating on vastly different timescales. Organic molecules embedded within ice particle interiors may remain stable for millions to billions of years, protected from radiation damage by overlying layers of ice, while surface molecules experience continuous bombardment by energetic photons and charged particles that limit their survival to timescales of thousands to millions of years. The rings thus contain organic molecules with ages spanning orders of magnitude, creating chemical chronometers that record different epochs in the system's evolution. Modern astrobiological research increasingly recognizes that organic molecules in extreme environments, such as planetary ring systems, may provide insights into the chemical processes that operated during the earliest phases of solar system formation, when complex carbon chemistry first began to emerge from simpler starting materials. The presence of organics on ring particles demonstrates that prebiotic chemistry can occur and persist in environments dominated by vacuum, radiation, and electromagnetic fields, conditions that may have been common throughout the early solar system and that continue to characterize many regions of interplanetary space. The electromagnetic processing of organic molecules within Saturn's ring environment creates laboratory conditions for studying radiation chemistry under parameters impossible to achieve in terrestrial experiments. The continuous bombardment of organic-coated ice particles by charged particles with energies ranging from electron volts to mega-electron volts provides natural experiments in radiation-induced chemistry that operate over spatial scales spanning hundreds of thousands of kilometers and temporal scales spanning millions of years. The rings thus serve as cosmic chemical reactors where organic synthesis and destruction processes achieve steady-state conditions that may illuminate the chemical pathways responsible for organic molecule formation throughout the universe. Perhaps the organic molecules coating ring particles represent more than simple chemical contamination. They may constitute a form of cosmic memory, preserving molecular signatures from the birth of the solar system in chemical archives that orbit Saturn with the mathematical precision of celestial clockwork. These molecules carry information encoded in their atomic structures about temperatures, pressures, and radiation fields that existed billions of years ago, when the solar nebula first began to condense into the planets and moons that populate our cosmic neighborhood. Only the universe could design a library system where the history of prebiotic chemistry remains accessible through spectroscopic analysis of ice particles tumbling in the vacuum of space, their organic cargo testifying to chemical processes that once operated throughout the birthplace of worlds. Through Saturn's ring system, spiral patterns propagate outward from their points of origin with the mathematical certainty of waves traveling through water. Yet these density waves move through a medium composed of countless individual ice particles orbiting in vacuum, each following its own precise elliptical path while participating in collective behaviors that span distances greater than the diameter of Earth's orbit around the Moon. These waves carry angular momentum and energy across the ring system at velocities determined entirely by the gravitational physics of orbital motion, creating structures that persist for years or decades while continuously reshaping the distribution of ring material according to principles that govern wave propagation throughout the cosmos. The spiral density waves originate at locations where ring particles experience gravitational resonances with Saturn's moons, creating periodic disturbances that organize into coherent wave patterns through the same mechanisms that shape spiral arms in galaxies and create interference patterns in quantum mechanical systems. When ring particles orbit Saturn at distances where their orbital periods relate to Moon orbital periods through simple mathematical ratios, they experience regular gravitational tugs that gradually accumulate into large amplitude disturbances capable of propagating throughout the surrounding ring material as coordinated variations in particle density and orbital velocity. Computer simulations reveal the intricate physics governing density wave propagation with precision that allows astronomers to predict wave behavior across spatial scales, ranging from kilometers to hundreds of thousands of kilometers, and temporal scales spanning years to centuries. Each wave represents a traveling disturbance in the gravitational field created by ring particles themselves. As regions of enhanced density generate stronger gravitational attractions that influence the orbital motions of particles in adjacent regions. The waves thus represent self-consistent solutions to the gravitational many-body problem, where millions of orbiting objects collectively create the gravitational environment that determines their own future evolution. The spiral structure of these density waves emerges from the differential rotation of Saturn's ring system, where particles closer to the planet orbit faster than those farther away according to Kepler's laws of planetary motion. This velocity shear transforms initially radial disturbances into tightly wound spiral patterns that appear to rotate around Saturn while actually representing wave crests and troughs that propagate outward through ring material at constant speeds. The mathematical beauty of this process demonstrates how simple physical laws can create patterns of extraordinary complexity and regularity through their operation over cosmic scales and geological timescales. Observational techniques for studying density waves rely on their effects on the optical properties of ring material. As regions of enhanced particle density appear brighter in reflected sunlight, while regions of depleted density appear darker. High-resolution images from spacecraft reveal spiral wave patterns with wavelengths ranging from a few kilometers to hundreds of kilometers. Their amplitudes and propagation speeds encoding information about the physical properties of ring material, such as particle size distributions, collision frequencies, and the efficiency of momentum transfer between neighboring particles during gentle impacts. The propagation velocities of density waves provide direct measurements of fundamental ring properties that cannot be determined through any other observational technique. Wave speeds depend on the surface density of ring material, the total mass per unit area, and the velocity dispersion of ring particles, which reflects the random motions superimposed on their regular orbital velocities. By measuring how fast waves travel through different regions of Saturn's rings, astronomers can map variations in ring mass and internal dynamics with spatial resolution approaching individual wavelengths, typically a few kilometers or less. The mathematical theory describing density wave propagation in planetary rings draws from diverse fields, including fluid mechanics, plasma physics, and stellar dynamics, creating a rich theoretical framework that connects ring dynamics to fundamental processes operating throughout astrophysics. The waves represent solutions to differential equations that govern the collective behavior of gravitationally interacting particle systems, with applications ranging from the dynamics of asteroid belts to the formation of spiral structure in galactic disks. Saturn's rings thus serve as natural laboratories for testing theoretical predictions about wave phenomena that operate on scales inaccessible to direct experimentation. Nonlinear effects in density wave propagation create phenomena that have no analog in conventional wave physics, as the waves themselves modify the medium through which they travel by redistributing ring material and altering local gravitational fields. Strong waves can create shock-like structures where particle densities change abruptly across narrow transition regions, while weaker waves may undergo dispersion effects that cause different wavelength components to propagate at different speeds, gradually spreading wave packets across ever larger regions of the ring system. The interaction between multiple density waves creates interference patterns of extraordinary complexity. As waves generated by different gravitational resonances overlap and combine according to principles of linear superposition modified by the nonlinear dynamics of ring-particle collisions. These interference effects can create regions where waves reinforce each other to produce enhanced density variations, or cancel each other to create zones of reduced wave activity. The resulting patterns evolve continuously as waves with different propagation speeds gradually shift their relative phases, creating temporal variations in ring structure that unfold over periods ranging from months to decades. The long-term evolution of density waves provides insights into the mechanisms responsible for angular momentum transport within planetary ring systems. As the waves carry angular momentum outward from their resonant generation sites toward the outer edges of the ring system, this angular momentum transport affects the overall evolution of ring structure over geological timescales, potentially contributing to the gradual spreading of ring material that may ultimately determine the lifetime of planetary ring systems around giant planets throughout the solar system and beyond. Some density waves show evidence for reflection and refraction effects when they encounter sharp boundaries in ring structure, such as gap edges or transitions between regions with different particle size distributions. These wave interactions create standing wave patterns and resonant cavity effects that can trap wave energy within specific regions of the ring system, leading to enhanced density variations and potentially affecting the formation of narrow ringlets and other fine-scale ring structures that remain stable over periods much longer than the wave propagation timescales. Modern theoretical models suggest that density waves may play crucial roles in the formation and maintenance of some of the most enigmatic features in Saturn's ring system, including the spoke patterns in the B ring, the braided structure of the F ring, and the propeller disturbances created by embedded moonlets. The waves provide mechanisms for coupling local disturbances to global ring dynamics, creating feedback systems that can amplify small perturbations into large-scale structural changes or maintain existing patterns against the randomizing effects of particle collisions and electromagnetic interactions. The study of density waves in planetary rings has revealed universal principles of wave propagation that apply to astrophysical systems ranging from protoplanetary disks around young stars to the spiral arms of galaxies, demonstrating how mathematical patterns emerge from gravitational interactions operating across vastly different scales of space and time. Saturn's rings provide a unique natural laboratory where these wave phenomena can be observed directly and studied in detail, offering insights into fundamental processes that shape the evolution of cosmic structures throughout the universe. Perhaps the spiral waves themselves represent a form of gravitational music, harmonic patterns in space and time that encode the mathematical relationships governing orbital motion in compositions that play across geological ages. Their wave crests and troughs marking time like the tick of a cosmic metronome that measures the pulse of gravitational forces operating with the precision of celestial clockwork across distances that span the boundaries between worlds. Hidden within the mathematical architecture of Saturn's current ring system lies evidence for a more popular satellite family that once orbited the giant planet. Their gravitational signatures preserved in the spacing and structure of ring features despite the physical destruction of the moons themselves millions or billions of years ago. Computer simulations reveal that Saturn's rings contain far too little mass to account for the complex gravitational resonances and structural patterns observed throughout the system, suggesting that additional moons once existed at specific orbital distances where their gravitational influences shaped ring dynamics before catastrophic events removed them from the Saturn system entirely. The missing mass problem emerges from careful analysis of the gravitational resonances that create gaps and density variations throughout Saturn's rings, as many of these features appear to be maintained by gravitational influences from objects that no longer exist. Theoretical calculations indicate that Saturn's ring system should contain at least twice its observed mass to support the current population of narrow gaps, spiral density waves, and other resonant structures through gravitational interactions with known moons alone. This mass deficit suggests that vanished moons once provided the gravitational architecture that continues to shape ring structure long after the moons themselves disappeared through collisional destruction or orbital evolution that carried them beyond Saturn's gravitational influence. Archaeological astronomy applied to Saturn's ring system reveals ghostly fingerprints of these vanished worlds encoded in the mathematical relationships between ring features and the orbital periods of surviving moons. Some gaps appear to be maintained by gravitational resonances with objects that should orbit at specific distances where no moons currently exist, creating cosmic fossil records of satellite populations that shaped ring evolution during earlier epochs of the Saturn system's history. These resonant ghosts demonstrate how gravitational influences can persist long after their sources vanish, maintained by the orbital memory embedded in ring particle trajectories that continue to avoid certain regions of space for millions of years after the original perturbing objects disappeared. The collisional destruction scenario offers the most plausible mechanism for removing substantial mass from Saturn's satellite system while preserving the gravitational resonances that continue to influence ring structure. When moons experience catastrophic impacts with large comets or asteroids, the resulting debris spreads throughout the Saturn system according to the orbital dynamics prevailing at the moment of impact. Most collision fragments either escape Saturn's gravitational influence entirely or spiral inward to join the ring system. But the gravitational perturbations created during the destruction process can establish resonant relationships that persist indefinitely, even after all physical traces of the original moons have been removed or redistributed. Computer models of satellite system evolution reveal that Saturn may have lost several Mimas-sized moons over the past billion years through processes including tidal disruption, catastrophic impacts, and orbital instabilities triggered by gravitational interactions with other satellites. Each lost moon would have contributed its mass either to Saturn's ring system or to the population of irregular satellites that orbit the planet at large distances, while leaving behind gravitational signatures preserved in the orbital architecture of ring particles and surviving moons that continue to experience the phantom influences of vanished gravitational sources. The isotopic composition of Saturn's rings provides additional evidence for contributions from destroyed satellites, as ring particles show trace element signatures that suggest mixing of material from multiple sources with different formation histories. Some ring regions contain isotopic ratios that match those found in Saturn's current moons, while others show compositions that cannot be explained by any known objects in the Saturn system. These chemical fingerprints may represent the only remaining evidence for vanished moons whose destruction enriched the ring system with materials formed under different conditions or at different locations within the early solar nebula. The timing of satellite destruction events can be constrained through analysis of crater populations on surviving moons, which record the bombardment history of the Saturn system over geological time. Periods of enhanced impact activity, such as the late heavy bombardment that affected the inner solar system 3.8 billion years ago, may have triggered cascades of satellite destruction that fundamentally restructured Saturn's moon system while contributing substantial mass to the ring environment. The current ring system may thus represent a mixture of recently formed material from destroyed satellites and ancient debris that has survived multiple episodes of satellite system reorganization. Gravitational interactions between Saturn's moons operate on timescales that can lead to orbital instabilities and satellite ejection even without external perturbations such as large impacts. Computer simulations reveal that Saturn's current satellite system may not be stable over billion-year timescales, as gravitational resonances between moons can gradually pump up orbital eccentricities until some satellites either collide with each other or escape the Saturn system entirely. These orbital evolution processes suggest that satellite destruction represents an ongoing phenomenon rather than a consequence of specific catastrophic events, implying that Saturn's moon population may continue to decline over geological time. The discovery of co-orbital satellites such as Janus and Epimetheus, which periodically exchange orbits through close gravitational encounters, demonstrates that Saturn's satellite system continues to evolve dynamically in ways that could lead to future collisions or orbital disruptions. These moon pairs represent possible precursors to the catastrophic events that may have destroyed earlier satellites, providing natural laboratories for studying the gravitational processes that determine satellite system stability over cosmic time. Their complex orbital dance illustrates how small perturbations can accumulate over millions of orbital cycles to produce dramatic changes in satellite system architecture. The search for additional vanished moons continues through detailed analysis of ring structure and dynamics, as each destroyed satellite should leave characteristic signatures in the gravitational environment that can be detected through careful study of resonant features and orbital spacing patterns. Advanced computer simulations incorporating millions of ring particles and complex gravitational interactions with known and hypothetical moons may eventually reconstruct the complete history of Saturn's satellite system, revealing when and how each vanished moon met its fate while contributing to the cosmic recycling processes that continue to shape planetary ring systems throughout the solar system. Modern theoretical models suggest that satellite destruction and ring formation represent fundamental aspects of giant planet evolution that operate throughout the cosmos, as the gravitational environments around massive planets create conditions conducive to both satellite capture and subsequent destruction through tidal forces, impact events, and orbital instabilities. Saturn's ring system may thus represent just one example of debris structures created through satellite destruction processes that operate around giant planets throughout the galaxy, creating temporary monuments to vanished worlds that encode the gravitational history of entire planetary systems in patterns of orbiting ice and rock. The mathematical precision with which ring resonances preserve evidence for vanished moons demonstrates how gravitational memory operates in celestial mechanical systems, where the influences of massive objects can persist long after the objects themselves have been destroyed or removed. Perhaps Saturn's rings serve as a cosmic graveyard where the gravitational ghosts of vanished moons continue to shape the orbital behavior of countless ice particles, their invisible influences creating patterns of order and chaos that testify to the dynamic history of a satellite system that once contained worlds we can now detect only through the mathematical archaeology of resonant gaps and spiral density waves. Only the universe could design a memorial system where the destruction of moons creates beauty that persists across geological ages, transforming catastrophic loss into orbital architecture that dances with the mathematical precision of celestial mechanics while preserving the gravitational memories of worlds that vanished into cosmic darkness, eons before human eyes first glimpsed Saturn's magnificent rings. Among Saturn's ring structures, none displays such restless complexity as the F-ring, a narrow band of ice and debris that writhes and transforms continuously like a cosmic serpent caught between the gravitational influences of its shepherd moons. This enigmatic ring defies simple description, its braided strands appearing to twist around each other in patterns that change hourly, creating kinks, clumps, and streamers that emerge and dissolve according to dynamics that challenge fundamental understanding of how ring material should behave under the orderly influence of orbital mechanics alone. The F-ring occupies a unique position within Saturn's ring system, orbiting at a distance where gravitational forces from the shepherd moons, Prometheus and Pandora, create an environment of perpetual instability rather than the mathematical tranquility that characterizes most ring regions. Located just 3,000 kilometers beyond the outer edge of the main ring system, the F-ring exists in a gravitational boundary zone where the competing influences of multiple moons create resonant interactions that pump energy into ring particle orbits, preventing them from settling into the circular, coplanar configurations that define stable ring structure elsewhere in the Saturn system. Computer simulations reveal that the F-ring's braided appearance results from gravitational encounters between ring material and embedded moonlets objects, ranging from tens of meters to several kilometers across that orbit within the ring itself. While continuously perturbing the trajectories of surrounding particles, these moonlets follow slightly elliptical orbits that cause them to periodically approach and recede from the ring's central core, creating periodic compression and rarefaction zones that appear as the twisted, rope-like structures visible in high-resolution images. The braiding process operates like cosmic weaving, where moonlets serve as gravitational shuttles that thread ring material into complex three-dimensional patterns. The temporal evolution of F-ring structure occurs on timescales ranging from hours to years, as different physical processes operate at different rates to continuously reshape the ring's appearance. Gravitational interactions with shepherd moons create large-scale changes in ring orbit and overall structure over periods of months to years, while encounters with embedded moonlets produce localized disturbances that evolve over hours to days. The superposition of these multi-scale dynamics creates patterns that never quite repeat, giving the F-ring an appearance of constant motion that distinguishes it from the relatively static structures found elsewhere in Saturn's ring system. Collisional processes within the F-ring operate under conditions that have no terrestrial analog, as ring particles experience both gentle gravitational shepherding and violent impacts with objects ranging from dust grains to house-sized boulders. The ring's narrow width, typically only 50 kilometers across, concentrates these collisional interactions within a confined volume where individual impact events can create disturbances that propagate throughout the entire ring structure. Large impacts can temporarily disrupt entire sections of the ring, creating gaps and clumps that gradually heal through gravitational processes, operating over timescales of days to weeks. The discovery of transient features within the F-ring provides evidence for ongoing impact events that create temporary structures lasting from hours to months before dispersing into the general ring population. Some of these features appear as bright knots or streamers that extend hundreds of kilometers from the main ring core, while others manifest as dark gaps that temporarily interrupt the ring's continuity. The ephemeral nature of these structures demonstrates that the F-ring exists in a state of continuous creation and destruction, with new features constantly forming while older ones fade into invisibility through dispersal and gravitational smoothing. Spectroscopic analysis reveals that F-ring particles consist primarily of water ice similar to that found throughout Saturn's ring system, but with subtle compositional variations that suggest mixing of material from multiple sources. Some regions show enhanced concentrations of rocky debris that may originate from meteoroid impacts on embedded moonlets, while others display organic contamination signatures that could result from bombardment by charged particles accelerated within Saturn's magnetosphere. These compositional heterogeneities create local variations in optical properties that contribute to the ring's complex photometric behavior and time-variable appearance. The electromagnetic environment surrounding the F-ring differs significantly from conditions within the main ring system, as the ring's location places it within regions of Saturn's magnetosphere where charged particle populations and magnetic field configurations create enhanced electromagnetic activity. Electrostatic charging of ring particles may contribute to the formation of temporary structures through forces that can overcome gravitational attractions between small particles, allowing electromagnetic repulsion to create localized dispersal of ring material that appears as temporary gaps or enhancements in ring density. Gravitational resonances with outer satellites such as Atlas and Pan create periodic perturbations that influence F-ring structure over timescales comparable to the satellite's orbital periods, typically ranging from days to weeks. These resonant interactions can trigger the formation of spiral density waves within the ring that appear as periodic brightness variations rotating around Saturn with the ring material. The waves represent traveling disturbances that carry energy and angular momentum through the ring system, potentially contributing to the long-term evolution of F-ring structure through processes that operate over thousands to millions of orbital cycles. The F-ring's role in Saturn's overall ring evolution remains largely mysterious, as this dynamic structure may represent either a transitional phase in ring development or a steady-state configuration maintained by the balance between creation and destruction processes. Some theoretical models suggest that the F-ring serves as a source region for material that gradually migrates inward to replenish the main ring system, while others propose that it represents a capture zone for debris ejected from impacts on nearby moons or from meteoroid bombardment of the outer ring regions. The study of F-ring dynamics has revealed fundamental principles governing the behavior of narrow ring systems that apply to structures found around other giant planets and potentially to debris disks around other stars. The complex interplay between gravitational shepherding, collisional evolution, and electromagnetic effects that characterizes F-ring behavior provides insights into processes that may operate in any environment where small particles orbit massive objects under the influence of multiple perturbing forces. These insights have applications ranging from the study of planetary ring systems throughout the solar system to theoretical investigations of debris disk evolution around young stars where planetary systems may be forming. Modern observations continue to reveal new aspects of F-ring complexity, including evidence for seasonal variations that correlate with changes in Saturn's distance from the Sun and the orientation of the ring plane relative to solar illumination. These seasonal effects may influence collision rates, electromagnetic charging processes, or the efficiency of gravitational interactions with shepherd moons, creating cycles of activity that unfold over timescales comparable to Saturn's 29.5-year orbital period around the Sun. The F-ring thus represents a natural experiment in multi-scale dynamics where gravitational, collisional, and electromagnetic processes interact to create structures that embody the mathematical complexity possible when simple physical laws operate under conditions of sustained instability. Perhaps the F-ring's restless dynamics serve as a reminder that cosmic order and cosmic chaos often coexist within the same gravitational system, where the mathematical precision of orbital mechanics can create conditions that support perpetual change rather than static perfection. The braided structures that appear and vanish within this narrow band of ice and debris demonstrate how gravitational forces can weave complexity from simplicity, creating patterns that challenge human understanding while following physical laws as fundamental as those governing planetary motion itself. Only the universe could design a cosmic rope that ties itself into knots using nothing more than gravity and time. Its twisted strands encoding the dynamic history of gravitational interactions, too complex for complete mathematical description, yet beautiful enough to inspire wonder across the vast distances that separate Saturn's rings from the terrestrial observers who study their eternal dance. Across the vast timescales of Saturn's 29.5-year journey around the Sun, the ring system experiences seasonal transformations that unfold with the geological patience of ice ages, as the planet's tilted axis carries the rings through cycles of illumination and shadow that alter their thermal environment, electromagnetic properties, and dynamic behavior in ways that connect the mathematical precision of orbital mechanics to the slow rhythms of planetary climate change. These seasonal variations operate on timescales that dwarf human experience, creating changes so gradual they remain invisible to casual observation, yet profound enough to reshape ring structure and influence atmospheric circulation patterns throughout the entire Saturn system. The ring's seasonal cycle begins with their orientation relative to the Sun, as Saturn's axial tilt of 26.7 degrees creates conditions where the ring plane alternately faces toward and away from solar illumination with each half of the planet's orbital period. During Saturn's northern summer, which lasts approximately 7 Earth years, the northern face of the ring system receives direct solar heating, while the southern face remains in perpetual shadow cast by the rings themselves. This asymmetric illumination creates temperature gradients across the ring plane that drive subtle circulation patterns in the tenuous atmospheres surrounding individual ring particles, and influence the efficiency of processes such as water-ice sublimation and organic molecule formation. The thermal consequences of seasonal illumination changes propagate throughout Saturn's atmospheric system through mechanisms that couple ring heating to global circulation patterns within the planet's thick atmosphere of hydrogen and helium. When ring particles absorb enhanced solar energy during summer seasons, they radiate this thermal energy as infrared radiation that can be absorbed by atmospheric gases in Saturn's upper atmosphere, creating heating patterns that influence convection and jet stream formation thousands of kilometers below the ring plane. These atmospheric changes can affect the generation of Saturn's magnetic field through magnetohydrodynamic processes operating within the planet's metallic hydrogen interior, creating feedback loops that connect ring thermal dynamics to electromagnetic phenomena throughout the Saturn system. Computer models of seasonal ring evolution reveal that thermal cycling drives changes in ring particle size distributions through freeze-thaw processes that operate over decades rather than the daily cycles that characterize terrestrial weather. During periods of enhanced solar heating, increased sublimation rates cause ring particles to lose mass through direct conversion of ice to water vapor, while subsequent cooling phases promote the accretion of new ice layers as water molecules refreeze onto particle surfaces. These seasonal growth and erosion cycles gradually alter the optical properties of ring material, creating brightness variations that can be detected through careful photometric observations spanning multiple Saturnian seasons. The electromagnetic environment within Saturn's ring system also varies seasonally as changes in solar ultraviolet radiation flux affect the charging of dust particles and the formation of ring spokes. Enhanced solar activity during Saturn's perihelion passages. When the planet approaches closest to the Sun in its slightly elliptical orbit, increases the intensity of charged particle interactions within the magnetosphere and may trigger more frequent spoke formation events. These electromagnetic seasonal effects operate through mechanisms that remain incompletely understood, involving complex interactions between solar wind variations, Saturn's magnetic field configuration, and the microscopic dust populations that create visible spoke structures through electrostatic levitation processes. Seasonal changes in ring dynamics extend to the gravitational interactions between ring material and Saturn's moons, as thermal expansion and contraction of the ring system can slightly alter the orbital distances at which gravitational resonances operate. These small changes in resonant relationships can trigger the formation or disappearance of narrow gaps within the ring system, create new spiral density wave patterns, or modify the efficiency with which shepherd moons maintain ring boundaries. The cumulative effects of these seasonal gravitational perturbations may contribute to long-term evolution of ring structure over timescales spanning multiple Saturnian years. Observational studies of Saturn's rings reveal seasonal brightness variations that reflect changes in both ring particle properties and viewing geometry, as Saturn's orbital motion continuously alters the angle at which Earth-based telescopes observe the ring system. The rings appear brightest when viewed at maximum opening angle during Saturn's solstice seasons, when their full three-dimensional structure becomes visible from Earth's perspective. During equinox seasons, when the ring plane aligns edge-on to both Earth and the Sun, the rings nearly disappear from view despite containing the same total mass of material, demonstrating how seasonal geometry affects the apparent properties of cosmic structures across interplanetary distances. The influence of seasonal changes extends to Saturn's atmospheric circulation through shadow patterns cast by the rings onto the planet's upper atmosphere, creating temperature variations that drive convective processes and influence the formation of cloud systems and storm patterns. During northern summer, the rings cast shadows across Saturn's southern hemisphere, cooling atmospheric regions that would otherwise receive direct solar heating and creating circulation patterns that transport heat and momentum between different atmospheric layers. These ring shadow effects operate like cosmic weather systems that modify planetary climate on scales comparable to the Great Red Spot on Jupiter or the seasonal polar caps on Mars. Chemical processes within Saturn's ring system also exhibit seasonal variations, as changing radiation environments affect the formation and destruction rates of organic molecules on ring particle surfaces. Enhanced solar ultraviolet radiation during summer seasons accelerates photochemical reactions that can both create complex organic compounds through radiation chemistry and destroy existing molecules through photodissociation processes. The balance between these competing chemical pathways varies seasonally, potentially creating cyclic changes in the organic inventory preserved within ring material over periods spanning decades to centuries. The discovery of seasonal ring phenomena has provided insights into the physical mechanisms governing ring evolution and the coupling between ring dynamics and planetary atmospheric systems that apply to giant planets throughout the solar system and beyond. Seasonal variations in ring opacity, spoke formation rates, and thermal emission properties demonstrate that planetary ring systems respond to external forcing on multiple timescales. From the rapid electromagnetic processes that create spokes within hours to the gradual thermal and gravitational effects that unfold over decades of orbital evolution. Modern theoretical models suggest that seasonal ring dynamics may play important roles in determining the long-term stability and evolution of planetary ring systems, by providing mechanisms for energy and angular momentum transport that operate on intermediate timescales between the rapid collisional processes that govern ring particle interactions and the geological processes that determine overall ring system lifetime. Seasonal forcing may help maintain ring structures against dispersal through electromagnetic and collisional effects, or conversely may contribute to ring evolution by driving systematic changes in particle orbits that accumulate over multiple seasonal cycles. The study of Saturn's ring seasons has revealed universal principles governing the response of orbital debris systems to periodic environmental changes that may apply to debris disks around other stars, where seasonal variations could be driven by orbital eccentricity, stellar activity cycles, or interactions with planetary companions. These seasonal effects represent natural experiments in disk dynamics that operate under conditions impossible to reproduce in laboratory settings, providing insights into fundamental processes that shape the evolution of circumstellar material throughout the galaxy. Perhaps the seasonal rhythms of Saturn's rings serve as a cosmic reminder that even the most mathematically precise orbital systems remain connected to the larger dance of planetary motion around their parent stars, their apparent permanence masking slow changes that unfold according to cycles too vast for human perception, yet as regular as the progression of terrestrial seasons. The rings thus embody the intersection between cosmic order and cosmic change, their seasonal transformations encoding the complex relationships between orbital mechanics, thermal physics, and electromagnetic dynamics in patterns that play out across decades while maintaining the essential architecture that makes Saturn's ring system one of the most beautiful and enduring sights in the entire solar system. Only the universe could orchestrate seasonal changes so subtle they require decades to complete, yet so profound they influence every aspect of ring behavior, from individual particle temperatures to global circulation patterns that connect orbital debris to planetary atmospheres across distances spanning hundreds of thousands of kilometers and timescales spanning geological ages. In the empty space between Saturn's rings and its innermost moons lies an invisible boundary that governs the very existence of the ring system itself, the Roche limit. A mathematical frontier where tidal forces achieve perfect balance with gravitational attraction, preventing ring material from coalescing into new moons while simultaneously defining the maximum distance at which solid objects can survive intact within Saturn's gravitational embrace. This boundary exists not as a physical barrier, but as a consequence of fundamental physics, operating with the quiet authority of natural law to maintain the delicate architecture that preserves Saturn's rings as discrete particles rather than allowing them to collapse into larger bodies or disperse entirely into interplanetary space. The Roche limit emerges from the competition between two gravitational influences acting on every particle within Saturn's ring system, the planet's gravity, which attempts to pull ring material towards Saturn's center, and the differential tidal forces that arise because Saturn's gravity decreases with distance according to the inverse square law. Ring particles closer to Saturn experience stronger gravitational attraction than those farther away, creating tidal stresses that stretch any extended object in the radial direction while compressing it in the tangential direction, like cosmic hands pulling and squeezing simultaneously with forces that increase rapidly as objects approach the planet's surface. For ring particles orbiting within the Roche limit, these tidal forces exceed the self-gravity that would otherwise allow small objects to stick together when they collide, ensuring that ring material remains forever fragmented into pieces ranging from dust grains to house-sized boulders that cannot aggregate into larger structures despite countless gentle collisions over millions of years. The limit thus serves as a cosmic preservation zone where the violence of tidal disruption maintains the peaceful coexistence of billions of ice particles tumbling through vacuum in mathematical harmony, their individual orbits as precise as planetary motion, yet forever prevented from joining together to form the moons they might become in other gravitational environments. Computer calculations reveal that Saturn's Roche limit occurs at approximately 2.44 times the planet's radius, or about 147,000 kilometers from Saturn's center, a distance that encompasses the entire main ring system while excluding all of Saturn's major moons except for a few small objects like Pan and Daphnis that survive within ring gaps through mechanisms that remain incompletely understood. The mathematical precision of this boundary demonstrates how fundamental physics creates sharp transitions in cosmic environments, establishing rules that govern the behavior of matter across spatial scales ranging from individual particles to entire planetary systems with the same mathematical certainty that governs atomic interactions. The physics governing the Roche limit applies not only to ring particles, but to any object attempting to orbit within the critical distance, including asteroids, comets, or artificial spacecraft that venture too close to Saturn's gravitational embrace. Objects larger than a few kilometers across would experience tidal stresses exceeding the strength of most geological materials, causing them to fragment into debris that would either spiral inward towards Saturn or disperse outward to join the ring system, depending on the specific dynamics of the disruption event. The limit thus represents a cosmic meat grinder that processes incoming material with the efficiency of industrial machinery, converting solid objects into the particulate matter that forms planetary ring systems throughout the solar system. The maintenance of ring structure within the Roche limit requires a delicate balance between the disruptive effects of tidal forces and the organizing influences of gravitational resonances, electromagnetic interactions, and collisional processes that create the complex architecture visible in high-resolution images of Saturn's rings. Without these organizing mechanisms, ring material would either collapse inward towards Saturn through orbital decay or spread outward through viscous evolution until it dispersed beyond the Roche limit, where tidal forces could no longer prevent particle aggregation into larger bodies. The current ring configuration thus represents a dynamic equilibrium maintained by competing physical processes operating with the precision required to preserve ring structure across geological timescales. The temporal evolution of material within the Roche limit follows pathways determined by the efficiency of various dissipation mechanisms that slowly drain energy and angular momentum from ring particle orbits. Inelastic collisions between particles convert orbital kinetic energy into heat and sound waves that radiate away into space, causing ring material to spiral gradually inward towards Saturn at rates measured in centimeters per million years. Electromagnetic interactions with Saturn's magnetic field and charged particle populations provide additional dissipation pathways that can accelerate orbital decay under certain conditions, particularly for the smallest dust particles that couple most efficiently to electromagnetic forces. The discovery of small moons orbiting within Saturn's ring system, such as Pan in the Encke Gap and Daphnis in the Keeler Gap, demonstrates that the Roche limit does not represent an absolute barrier to moon formation, but rather a threshold above which self-gravity can overcome tidal disruption under specific circumstances. These embedded moons survive within the nominally disruptive environment through mechanisms that may include rapid rotation that reduces tidal stresses, unusual internal structure that enhances cohesive strength, or locations within ring gaps where reduced particle bombardment allows gradual accretion to proceed faster than tidal erosion. The mathematical elegance of the Roche limit extends beyond its role in planetary ring dynamics to applications throughout astrophysics, where similar tidal limits govern phenomena ranging from the disruption of binary star systems to the feeding of material onto black holes and the formation of debris disks around young stars. The limit represents a fundamental boundary in gravitational systems that determines where solid objects can survive intact versus where they must exist as dispersed particle populations, providing a universal organizing principle that operates across cosmic scales from asteroid belt dynamics to galactic structure formation. Modern theoretical investigations of Roche limit physics have revealed complex phenomena that emerge when realistic material properties, rotation effects, and electromagnetic forces are included in the analysis beyond the simple point mass assumptions used in classical derivations. These advanced models show that the effective Roche limit can vary significantly depending on object composition, internal structure, and environmental conditions, creating a more nuanced picture of tidal disruption processes that helps explain the diversity of ring structures observed around the giant planets in our solar system. The long-term fate of Saturn's ring system remains intimately connected to processes operating near the Roche limit, as the continuing inward migration of ring material will eventually carry most particles to distances where tidal forces become so strong that even the smallest fragments cannot maintain coherent orbits. This ultimate destiny represents the final chapter in ring evolution, when the mathematical boundaries established by tidal physics will reclaim all the material currently preserved within Saturn's magnificent ring system, transforming orbiting ice particles into atmospheric entries that will rejoin the planet from which gravitational forces first separated them millions or billions of years ago. Perhaps the Roche limit serves as a cosmic reminder that even the most beautiful structures in the universe exist within boundaries established by fundamental physics, their apparent permanence depending on mathematical relationships that operate with the inexorability of natural law, yet allow for the temporary emergence of complexity and beauty within precisely defined limits. The invisible boundary that preserves Saturn's rings demonstrates how physical principles can create conditions that support neither complete order nor complete chaos, but rather the delicate balance that allows billions of ice particles to dance in mathematical precision while remaining forever prevented from joining together to form the worlds they might become under different gravitational circumstances. Only the universe could design preservation through prevention, maintaining cosmic beauty by establishing limits that ensure ring particles remain eternally separated, yet gravitationally bound, their individual orbits as precise as clockwork, while their collective destiny remains written in the mathematical certainty of tidal physics operating across distances measured in hundreds of thousands of kilometers and timescales measured in geological ages that stretch beyond human comprehension into the cosmic future where all boundaries eventually dissolve into the silence of universal equilibrium. In the profound stillness that exists between the mathematical certainties of orbital motion and the quantum uncertainties that govern matter at its smallest scales, Saturn's rings continue their eternal dance through vacuum and time, each ice particle following trajectories as precise as the equations that describe planetary motion, yet as ephemeral as frost forming on a winter window. The cosmic clockwork that maintains their orbits operates without sound, without friction, without the slightest awareness of the beauty it creates through nothing more than the patient application of gravitational forces across distances that span the space between worlds. The mysteries hidden within these rings, the electromagnetic spokes that appear and vanish like thoughts in a planetary mind, the braided structures that twist through space in patterns too complex for complete mathematical description, the gravitational memories of vanished moons that continue to shape ring architecture long after their physical destruction. These phenomena remind us that the universe creates complexity through simplicity, weaving intricate patterns from the fundamental forces that govern all matter and energy throughout the cosmos. As Saturn completes another rotation, carrying its rings through another 10-hour cycle of shadow and sunlight, the system continues its slow evolution toward an uncertain future where tidal forces will eventually reclaim all orbiting material, transforming the ring particles back into atmospheric gases that will rejoin the planet's vast interior. Yet, for now, in this cosmic moment that spans millions of human lifetimes, the rings persist as monuments to the mathematical beauty that emerges when physical laws operate across scales of space and time that dwarf terrestrial experience. The silence between ring particles contains infinities, vast empty volumes where only gravitational fields and electromagnetic radiation traverse the darkness, carrying information and energy at the speed of light while ring material tumbles through vacuum at velocities measured in kilometers per second, yet appearing motionless to distant observers who witness only the serene majesty of Saturn's eternal crown of ice and mathematics. In this quietude that spans astronomical distances and geological ages, the rings drift toward their inevitable destiny with the patience of cosmic time itself. Their current beauty, representing just one frame in a motion picture that began with the catastrophic destruction of ancient moons and will end with the gradual spiral of all ring material into Saturn's atmospheric embrace, completing cycles of creation and destruction that operate on timescales as vast as the emptiness between the particles themselves. And in that emptiness, in the mathematical spaces between orbiting ice crystals, the universe rests in perfect silence, dreaming gravitational dreams that manifest as ring systems around distant planets, their beauty visible across interplanetary distances, yet comprehensible only through the patient application of physics and mathematics to phenomena that exceed human intuition while remaining forever bound by natural laws, as eternal and unchanging as the cosmic background radiation that fills all space with the fading echoes of creation itself. Sleep well.